Okay, guys. You can complete that quiz on your own. The answer key to that quiz is posted on YouTube. Okay, it's a video of me going through the quiz. All right. Hopefully this will give you an idea of how you're doing going into the test on Monday. Okay. Again, the answer key is by video posted on YouTube. Let's get started with today. Okay, guys, we skipped one thing we need to go back and cover on the alkane handout. Alkanes, cycloalkanes. Condensed formulas at the top. And you look at this carbon atom substitution. Primary, secondary, tertiary, etc. It's analogous to like primary amines or primary amides. But we did not point this out. Look at this structure here. Primary carbons. Primary carbons are bonded to one other carbon. How many primary carbons in this compound here? That's a primary carbon. 1, 2, 3, 4, 5. They're going to be at the end of a chain because they're only bonded to one carbon. Five primary carbons. How many secondary carbons in this compound? Secondary carbon bonded to how many carbons? 2. How many carbons bonded to 2? That one's bonded to 2. Any other secondary carbons? Only one secondary carbon in this compound. How many tertiary carbons? Tertiary carbons bonded to 3 carbons. That guy right there is tertiary, bonded to 3 carbons. Any others? Only one tertiary carbon in this molecule. Quaternary carbons. A carbon can be quaternary. By the way, nitrogen can too, but if it is, it's going to have a charge. Quaternary carbons. How many in the compound? 1. Every carbon should have been classified according to this terminology. Right? Also applies to amines. That's a secondary amine, right? It's a primary amide. Nitrogen bonded to one carbon in the primary amide. We can also classify hydrogens. Hydrogens are classified according to what type of carbon they're on. Because all hydrogens only have one bonded carbon, if they're bonded to carbon at all. So that cannot distinguish it. We call it a primary CH, is referring to a hydrogen that's on a primary carbon. A tertiary CH is referring to H's that are on tertiary carbons. How many primary CHs in this molecule? It's the same molecule as above. How many primary CHs? 15. Because each primary carbon, which there's 5 of those, has 3 H's. Yes, 15. How many secondary CHs? Well, how many H's are on secondary carbons? It's only one secondary carbon, correct? How many H's there? 2. How many tertiary CHs? One tertiary carbon. How many H's on that carbon? 1. How many quaternary CHs? No such thing, because a quaternary carbon cannot also be bonded to an H. It would have 5 bonds. There's 18 hydrogens in this molecule. The 18 have been classified this way. Last thing at the bottom, and this takes us into alkene reactions. With alkenes, we will see lots of reactions. Did I say lots of reactions? I think I did. That's okay, because there's nothing you can't do. And I was only joking, right? Nothing you can't do. Well, there's some things. I can't jump and touch that ceiling. I know I can't, and I never would. Combustion of alkanes. Alkanes are pretty unreactive. Can't do much chemistry with them. But you can burn them. And that's a very important reaction, right? We burn like butane. Has anybody ever burned butane? You got a butane lighter? You burn in butane when you give it a little spark. Reacting with oxygen, combustion, right? All the carbons are converted to CO2, all the H's to water, and you produce some heat. Exothermic. You could actually do some calculations there to determine how much heat is released. But we can burn other alkanes as well. This is a radical reaction. We will not be looking at many radical reactions, although at the end we will look at some. About the only other reaction of alkanes is, this is radical oxygenation, really. You can also do radical halogenation. Take an alkane, react it with an elemental halogen, usually we like light. The old days like sunlight. And we can get a substitution reaction here and produce HBr. That is a radical reaction. This tends to be very uncontrollable. It's going to go all the way to full oxidation. You can't stop it. Boom, it's done. This is more controllable, and we can get controlled products where the carbons are still intact. Up here, all the carbons are cleaved. We'll look at radical halogenation near the end of the course. That's about it for alkanes. Alkenes, on the other hand, a large amount of chemistry. Again, somebody left a lab coat in the lab lecture yesterday if anybody wants to claim it. Green handout is our outline. Okay, we're ready to start test 2 material. Before we do, let's talk about the test on Monday. Test will be very similar format as the quizzes you've seen. Short answer. Short answer questions in the workbook. You see my type of questions. There'll also be a few multiple choice. Topics. Well, everything since day one. What do we have? Lewis structures. Everything associated with that, DUS, charges, et cetera, et cetera. Then we had what? Physical properties. Yeah, melting point, boiling point, solubility. Then we went into acid-base chemistry. Yeah. Solubility, we had the IMFs. Physical properties, IMFs, acid-base chemistry. Then we moved on to alkanes, conformations, nomenclature. Yes, IR. IR will look like it is in the workbook. We'll also do a practice IR this afternoon, like we did yesterday. And any other miscellaneous topics that I did not mention, because I never can mention them all. But you know what we've covered. Any questions about the test? Typically 4 to 5 pages. And typically the first question for me is usually nomenclature, and in the back it'll be spectroscopy, this time IR. Questions about the test? Again, you need to arrive early, okay? People coming in will not, at 8 o'clock, 8:01, I would almost prefer just to lock the doors, okay? Because you cannot do well arriving at that time and expect to come in and be comfortable and do well on the test. You're also or disturbing other people who are here, ready to get focused, etc. Okay? We will need to spread out and make use of sides if anybody's willing to sit over there, etc. Last questions about the test. Okay. Test 2 material. Test 2 is largely alkenes and stereochemistry. You have an outline in green. Actually, I need to pass out other things, I reckon, for folks that did not get the thermodynamics yesterday in lab. Please do not take another one. Okay. This is for today's lab group. Friday lab only. Thursday lab has this. Another white handout. Intro to Alkenes. Friday lab only. Thursday lab has this. The intro. Okay. Is there other stack going around? Can I get one of those, please? Thank you. Everybody got a green one? Alkene reactions. I also sent you a handout by email, one to print for Wednesday. Okay? This sort of goes with that handout. This is the outline for our reactions. I want to orient you a little bit to the handouts, then we'll look at the thermodynamics handout, some content there. Warm up. These are some example line reactions. Predict the products. Many of my warm-ups are sort of a little bit kind of challenging, very thought-provoking. These, on the other hand, are very basic. These are intro. Okay? Very standard type questions for alkenes. For example, reacting alkenes with some type of acid, either sort of dry acid or aqueous acid. Okay? Halogen down there. But then there's other questions here. On the flip side of the green are our alkene reactions. Roman numeral 1 and 2. If you haven't already, please recognize that our handouts are supposed to give you organization. Okay? And when I say Roman numeral 1, please look at Roman numeral 1 and understand what this is describing. Too many times I see students who don't even know what this section's about because apparently you've never read Roman numeral 1. Okay? I expect you to read headings which are meant to be informative and include terminology that's important, etc. These up top are reactions with H+, that is an acid. The acid is the electrophile. That's an important word, or I wouldn't have used it in the heading. And these involve a carbocation. All of these involve a carbocation. That's free information right there. Okay? Down below, other reactions. But you can already tell that none of those involve a carbocation, right? Because it says it in the heading. All right? Then we have outline, okay, which I'll be going by, and that you can use to be reading ahead, etc., right? You know what we're going to be doing? In the back, This is a fairly new addition to the handout for me after 15 years of teaching, because I see this as hugely important. This is not going to be presented this way in a textbook. I'm not quite sure why. Two mechanisms for making nucleophile to carbon bonds. Okay? Both of these are described. I find these to be hugely important. And I'm telling you my version of the situation here. Okay? You're going to do well with reactions, you have to know mechanisms. To know mechanisms, you have to know what a mechanism is. And what is terminology, and how do you use arrows? But we've been using arrows with our acid-base mechanism. Yeah? So that's the start of it. But we'll continue with the same principles. The arrow has to mean something. A lone pair is making a bond to the carbocation. That's what the arrow means. A nucleophile is now bonded to this carbon as a result of that arrow. We'll have stereochemistry. The nucleophile can be forward or back. But why? Why can it be either? We need to understand why. Down below is a different type of mechanism. These are two general mechanisms that I highly recommend as a place to start. We will see this general stuff in just about any mechanism you do. I'll also give you some written information about mechanisms. Again, free information if you want it. All right. An overview, some words of caution, etc. And then there's warm-up on the mechanisms back here. A pretty more straightforward example, and then a little bit more challenging, but very doable. And if you spend time on it, very rewarding for advancing your understanding of mechanisms. That's the green handout. Okay. Intro to Alkenes contains your nomenclature. Nomenclature of alkenes covered by video only. It's a second separate video from alkanes. A little bit of intro at the top. We can have a very small alkene, the smallest alkene you can have. You've got to have two carbons to have a carbon-carbon double bond. Ethene. The ene ending comes from the fact that it has an alkene. So we don't call it ethane, we call it ethene. Nomenclature is going to be like that. Once you learn the fundamental nomenclature, it's just you just change it a little bit as you go along, based on the functional group. Now the slang name of this is ethylene. You've never heard that. And if you polymerize ethylene, what do you get? That's right, polyethylene. Ever heard of polyethylene? Common polymer. Anybody got a water bottle? Usually polyethylene or polypropylene. Yeah? All right, some info. But alkenes can also be part of larger molecules, like this alkene here in the breast cancer drug tamoxifen. Benzene rings, the pi bonds there, the alkenes there are not alkenes. Once they're aromatic, it has different chemistry. We don't call these alkenes. The alkene is there. All right. There's your nomenclature by video. The nomenclature will include EZ terminology, using E or Z to distinguish between stereoisomers. Somewhat analogous to cis and trans. We will use cis and trans here, but we'll learn that cis and trans doesn't always work. And you have to go to the EZ nomenclature. You have to spend a little time on it, just like anything. All right, you can do it. And you may even find that it's pretty easy. Okay. The remainder of that is not by video. We'll look at it at some point. It's a little bit miscellaneous, but very important. The physical properties is a lot of meat and potatoes there. The last two sheets are more miscellaneous, more the application. Okay? But still very important. Thermodynamics and kinetics. Okay, you guys from yesterday should have this already. Everybody else got it now? All right. Of course, none of this new material is on the test, right? All this new material is test 2 material. Yesterday, we looked at the first half of this, and we will do that this afternoon for the other group. All right? Thermodynamics. Let's move back to the kinetics, which begins at the very bottom on back here, but mainly that's just what you already know. And we'll be looking over here. Kinetics describes rate of the reaction, right? Speed of the reaction. How fast is the reaction? Rate. We're going to be doing lots of reactions, and so you got to review your thermodynamics, okay, which is more of your equilibrium and your exothermic, endothermic, that type of considerations. That doesn't tell you anything about the rate. For example, a diamond reacts with oxygen exothermically. Does that mean that it's going to react with oxygen? Do diamonds react? Anybody have a diamond? You store it in air. Does it react? So the rate is tremendously slow. It's so slow that it ain't happening. There's a difference between being favorable by thermodynamics versus the rate consideration, the kinetic consideration. Okay, one of the main things we'll be doing with kinetics is being able to show reactions by a reaction coordinate diagram. All right? You'll be asked to do these, like on lab reports, etc. It shows the progress of the reaction here and some type of energy here. I'll just usually just write energy. It can be very specific, but it really doesn't matter. It's not going to change the overall view of what's going on here. And a reaction starts with reactants and ends up with products. And we graph the energy as the reaction happens. Reactants could be me and you. Can you be the reactant? Let's react and let's make a bond. Here is us before we do anything. We have a certain energy. Okay? Here's us after we bonded. That's the products. It has a certain energy. But we have to keep in mind that there was something in between. For example, we have to initiate the bonding. And what did I do first? Well, if you notice, I stepped forward a little bit. And that took energy. So once I initiate, we can consider the energy along the pathway. And then I had to move my shoulder, and that took energy. Okay? And so all this is happening, and we can plot the energy. Finally, we get to the end. All right? But between, we had to do some movement, so the energy went up. We get to the end. All right? Let's look at some terminology, and what are we looking for here? First off, these two show a single reaction, no intermediate. We'll see intermediates below. No intermediate. For example, what if we want to make a bond? What if we want to make two bonds? Okay. Here's the end result. Here's the beginning. Well, maybe I'll first make this bond, and this is going to be called an intermediate. Then we move on and make the next one, a second step, two-step process leading to an overall reaction of making, okay? Let's look at the differences here. This one shows a reaction which is exothermic. Now, I typically will use delta H and say exothermic, endothermic. Here they're using delta G, which is a more broader term, right? And they're calling it exergonic. Did y'all use exergonic, endergonic? Okay. You can also do delta H. I'll typically do that, but not a big difference. I would just call this exothermic. On the other hand, this here is an endothermic reaction, because the products have energy higher than the starting, right? So that should make sense. Let's look at this set of reaction coordinate diagrams. Which reaction is most favorable here? 4 different reactions shown. They're all just one step. Sometimes you may call that one elementary step. There's no intermediate. We'll see intermediates below. Which reaction is most favorable? Most favorable to me is a thermodynamic term. Like it's favorable for a diamond, carbon, to react with oxygen. That's a favorable reaction thermodynamically. It don't mean it's going to happen, but it's favorable, or some people call it spontaneous. Is that right? I've had Gen Chem in many years. Then you say spontaneous. So are you telling me that a diamond spontaneously reacts with oxygen? No. It's a term that goes in quotations. It's favorable or spontaneous based on thermodynamics. Am I getting that right? Okay. Which reaction is most favorable or most spontaneous? Which one looks most favorable? Is this one the most favorable? No, it's endothermic. Endothermic is not favored. Which ones are exothermic? Are these two? That's a little bit hard to tell, but of the two, which is most favorable? This one, right? I mean, you get a ruler. You got this much exothermic. That's a value. It's a little bit hard to tell, but isn't that one more exothermic? Yeah, I would say that this one's most favorable thermodynamically because it's most exothermic. By the way, such value right here comes from bond calculations, which we did yesterday and we'll do today and this afternoon. Okay? That would be your delta H, which comes from calculations. And this would be negative something because it's exothermic. Right? Which favorable reaction is fastest? First off, which ones are favorable? Top two. Which one's going to be faster? A is faster. Why? Because rate has nothing to do with delta H or thermodynamics. Rate mainly is affected by what here? The energy of the transition state, right? That's a transition state. Sometimes called an activated complex. Have you ever heard that term? Transition state. That's if you could catch, we made that bond. Just take a snapshot right there. That's a transition state. It's not a discrete molecule. But there is a point where the transition state energy is the highest. And then as the bond is making, it sort of falls back down into that, this bond is made. We'll see more. Right? Kinetics. Kinetics is largely based on energy of transition states. Not this answer. Okay? This one's faster, but this one's most exothermic. This one's actually more favorable. Right? Difference between thermodynamics and kinetics. You should know all that. This is just a brief review. Let's look at the one below. The one below shows an intermediate. One intermediate. This alkene reacted with HBr to form this intermediate. It's a carbocation. We'll see this exact reaction and many variations of it. How many transition states in this overall reaction? This is an overall reaction. We say it's a two-step reaction. We can say it has two elementary steps to the overall reaction. It has one intermediate, See, the intermediate sits in an energy well because there's a transition state leading to the intermediate. Then there's a transition state leading to the final product. Intermediate usually sits in an energy well as a result. Okay? Did you see an intermediate up there? No, it was just one transition state. Okay? Typically, your intermediates in what we'll be looking at are going to be charged. That's not anything to memorize, that's just something to point out. You'll see, they'll always be charged. Beginning and end will typically be neutral. Okay? What else can we say there? Were there questions over here? Of the two steps, of the two elementary steps here, which one is rate determining? RDS, rate determining step. That would be the step with the highest climb, the highest activation energy. Right? Because this here is your E sub A activation energy for that step. All right? I never know how to draw this. Is the activation energy over here from there, or is it there?
The second one.
Second one? I tend to want to argue with that. Because which one's the hardest step? The first one's the hardest step. Okay? If you can do the first step, you can do the second step. Because there's enough energy here to do this. Okay? You only really need to be concerned about this. Can you meet this energy demand? So this would be the slow rate determining step, where the next step would be called fast. Okay? We just call that fast relative to the RDS. Number of transition states in this reaction coordinate diagram? 2. Basically, there's questions that could be asked. Do you understand what's going on with these? Can you draw them? Okay. One thing we can state is usually, I don't know usually because usually doesn't mean always. Like with everything, we're going to see some exceptions. But usually our first opening consideration is a lower energy species will usually have a lower activation energy leading to it. This is somewhat comes from the so-called Hammond postulate. Although it's not exactly the Hammond postulate, or it's sort of comes from that consideration. Lower energy species will have the lowest activation energy. Look at this. This starting can go to 2 different intermediates. That's what this is showing, and not showing the rest. Of the 2 intermediates, I think I can label these A and B. A has lower energy. Based on what we said up there, the transition state leading to A should be lower. That's what we said. Or the EA. The EA of the transition state, what we're looking at here, the activation energy of this step, should be lower. You see? Indeed it is. Because we will be able to determine the energy of these. This we're not going to be able to really determine. So this will not be here. You're going to have to show it yourself. But you show it based on this, that A should be lower. So when you draw it, you make A lower than B. That's what it's telling you to do here. Okay? Usually that's what you want to do. If we don't do it, we'll point out, hey, we're doing an exception here. It would be an exception for the activation energy to be higher for A. That would be weird. Okay? Here the difference in both of these are two different carbocations. We'll be looking at which carbocation do we want to form. Here, this cation is more stable because of inductive donation. We should be able to understand this and be able to predict carbocation stability based on what we've talked about thus far. Because we know sp3 carbons do what? Inductively. They donate. Right? How do you stabilize a cation? Do you want to move electrons towards it or pull away? You're a cation. How do I help you out? Electrons towards you. Same thing as saying you're poor. How do I help you out? Give you money. You're electron poor. How do I help you out? Give you electrons. Push electrons towards you. On the other hand, if you're rich, how do I help you out? I have to start borrowing money from you because you don't like being rich or poor. Okay? See, molecules don't like being plus or minus. They can, but everything prefers neutral. Most everything, until you want to have some exceptions. What's below? Oh, an exception! Already. Look at this. The first step is common. It forms a common intermediate. There's no difference. The second step is where you can get variation, or you have choice. You can either form this product or this product. This is called the 1,4. Once we get into this, it's called 1,2. The 1,4 product's more stable. You see that right here. It's lower in energy. Now, our postulate said that the transition state to this should be lower. Is that the case here? No. The transition state leading to this is higher. That's an exception. That's odd. So we have to recognize that it's against our opening statement. Now, why is the 1,4 product more stable? We haven't covered that yet. It's in some of the handouts, stability of alkenes. So we can talk about kinetics. If you're here and you have a choice, which one of these two is going to be formed faster? 1,4 or 1,2?
1,2.
1,2 will be formed faster because it's easier. Everybody agree that easier is going to be faster? Here you go. The 1,2 is thus your kinetic product. It's favored by kinetics. It's formed fastest. What about thermodynamically? Which one's favored thermodynamically? Thermodynamically, you're just looking at like exothermic, endothermic, overall. Which one is overall more favored? 1,4, the more stable one. The 1,4 is favored by thermodynamics, but the 1,2 is formed faster. Which one do you get from this reaction? It actually depends on how you perform the reaction. Because you can perform a reaction where thermodynamics rules, or you can perform a reaction, in this case, where kinetics rules. We'll be talking about that. This exact reaction type is covered during test 3. But when we cover it, we will already know all the stuff that's here. We'll just fill in the gaps. And I'll actually refer you back to this. I'll do a good bit of referring, and I'll go ahead and tell you. Sometimes I tell you, let's mark the date. What is this? Friday the 2nd? Near the end of class. That's when we talked about the exception and the 1,2, 1,4. All right, let's see if I can remember that. Because in like a month, I'll remind you about, remember Friday the 2nd? A lot of times you guys are going, don't do that. You got to remember. Right? Friday the 2nd, that's when we first saw it. Okay. Did we cover everything there? What else was on there? What's at the bottom? Anything to say here Does that reaction have any intermediates? There's no intermediate there, right? Let's see. Don't worry about what type of reaction it is. It's a reaction going from one molecule to another, or one molecule to. If this reaction was slow, for example, it took you 5 hours to do it, and you really wanted to leave early on Friday, you wanted to speed up your reaction. Well, that scenario doesn't work. Forget that. It doesn't work. How would you increase this reaction?
Catalyst.
You could add a catalyst. Okay. And what does a catalyst do?
Lowers the energy of activation.
It lowers the activation. What is the activation energy for this reaction? It looks like just one step. Right here, right? Yes. And if we added a catalyst, we would expect what would be the difference in our reaction according to the diagram. Maybe it would look like that instead. Right? We lower the energy. As the energy is lower, it's going to happen faster. Yes, catalyst could do that, and that works for leaving earlier. We'll see a little bit different twist. What I'm really getting at is, what if we had two different reactions? And they looked like this. And this was reaction A, and this was reaction, let's call this 1 and 2. Which reaction would be faster? Number 2 would be faster. In the end, we've pretty much have stated this, but it will come up, and I'll have to remind you about this. It's just a closing summary statement that's important. I think we've already described it. It's better to discuss it in context. Okay, let's see where we're at, guys. Nomenclature by video, our outline. What I sent you by email, you got to have on Wednesday. What's this? Thermodynamics, kinetics. We'll do the first half of this afternoon. On Wednesday, we will begin in earnest with alkene reactions. The handout I sent you, the outline is the green. There's your outline. Is that it, guys? Any last questions? We got a minute here. Any last questions about the test? Pencils. Let's take test 2. Pencil. Question? Wednesday? Sometimes I may, sometimes not. It depends on how things are going. Sometimes it's the day after. No Scantron. Multiple choice is just circled on there.